All right, guys, here we are, number 39. So the question says solid sodium chloride does not conduct electricity, but molten sodium chloride does. Explain this difference and outline what happens in an electrolytic cell during electrolysis of molten sodium chloride using carbon electrodes. So it's talking about the electrolytic cell, okay, not the voltaic one. The voltaic one is the one you guys did in the lab in class. We're talking about the electrolytic cell, the one that only happens in one beaker, and it does not need a salt bridge, and it requires energy. It doesn't produce energy, okay? So first part, why does the sodium chloride not conduct electricity if it's solid? Because it's solid, and therefore it's in a lattice, and the ions are close together and they're not moving, and the electrons need to be able to move. The ions need to be able to move around in order to conduct electricity. Now, if it's molten, so the word molten means melted. If it's melted, then the ions are free to move around, and therefore they are able to conduct electricity. Okay? Then it asks you to outline what happens in an electrolytic cell during the electrolysis of molten sodium chloride using carbon electrodes. So the carbon electrodes are going to be the inert electrodes we talked about. Remember, inert meaning that they are not very reactive at all. So carbon electrodes are not reactive. They are inert. You will want to explain that the positive ions are going to move towards the negative electrode, and that which would be in NaCl. Na is the positive ion, right? So Na is going to move to the negative electrode, and that the negative ions, the chlorine ions, are going to move to the positive electrode. Okay, so let me show you that on my paper, how I wrote it down. So outlining, it says Na plus ions move to the negative electrode, which is called the cathode. The negative ions move to the positive electrode, which is called the anode. All right. So what's happening is that Na plus gains electrons, and then it forms the sodium solid. Where? At the negative electrode, the cathode. Okay. And the chlorine ions, they actually will lose electrons, the 2 electrons, to form Cl2 gas. And that's going to form at the positive electrode called the anode. Okay, so that's how you explain that. So that's number 39. Next, you asked about 46I. Let's look at 46I. Okay, on 46, it says, draw a diagram of apparatus that could be used to electrolyze molten sodium bromide. Label the diagram to show the polarity of each electrode and the product formed. Okay, I want you to just basically go to your notes, right? And you're essentially just copying this down, but with potassium bromide, KBr. That's it. Okay? Or like that, right? So it's just the electrolytic cell is what it's saying. And so if I go back, let's see, where were we? Okay. Draw a diagram of the apparatus that could be used to electrolyze molten potassium bromide. Label the diagram to show the polarity of each electrode and the product formed. So watch, this is what I did. I literally just drew the quick little sketch of a beaker with 2 electrodes. I didn't label what they are because they're inert. On the top, there's a battery there, right? Battery. It has to provide electrons. The electrons are going to move in this direction. This side is going to produce the potassium solid, and this side is going to produce the bromine gas. So what do the reactions look like? They look like this. Look, the potassium is a positive ion, gains an electron, becomes solid potassium. Solid potassium. The bromine ions, that you need 2 of them to form the bromine diatomic molecule, right? You guys know Brinkelhoff. And so this is the reaction for that, and that forms here. Okay? And remember that the bromine is going to be formed at the positive electrode. So you'll want to label this as the positive electrode. Let me do that. Ugh. Okay, this is the positive electrode. And then the potassium is going to be formed at the negative electrode. So this is going to be the negative electrode. And the electrons flow through the wire ions, which move through the liquid. So electrons are moving. Okay, that's your electrolytic cell. That's 46I. So let's see. Okay, I've already addressed the rest of 46. Okay, and then you also wanted to know about 47. 47 talks about iodine, I with a negative charge. Okay, so again, let's make sure that we understand that that's a -1 charge. I, -1. We know that I is a negative ion, -1 ion. Reacts with iodate ions. This is IO3. You guys should know that iodate is IO3 with a -1 charge also. In acidic solution to form molecular iodine. Okay, you have to know that molecular iodine is a Brinkelhoff, that iodine exists as a diatomic. So that's I2 and water. So how did I draw it on my paper? Here's my iodine ion. Here's my iodate ion. And then my 2 products, iodine, which is a solid at room temperature, and water liquid. That's an L, in case you can't read that. Okay, next it says, determine the oxidation number of iodine in each iodine-containing species in this reaction. There's 3 iodine-containing species. There's I, which is -1. There you go. That's easy. There's IO3 with a -1 charge. So remember in the other videos how I taught you? We don't know the charge of I, but we know that there's 3 O's and each one is -2, which gives us -6. And overall it equals -1. So X plus -6 equals -1. Add 6 to both sides. You end up with X equals +5. So that is the oxidation number for that I. So this one's -1. This one is +5. And finally, remember we talked about like I2, it's not bonded to anything else. It's just 2 I's. It's neutral. It's in its elemental state. It's just molecular iodine. The oxidation state is 0. So there you go. 0 for that one. +5 for that I, and -1 for that I. Okay, then it says, and I think this is the last part of the question, it says, identify with a reason the species that undergoes oxidation and which one undergoes reduction. So look, I goes from I- to I2. That one's the one that gets oxidized because there's an increase in oxidation number, aka loss of electrons. IO3 with a negative charge goes to I2. That one is reduced. Why? Because there's a decrease in the oxidation number, which is a gain of electrons. So that answers that question.